So I would like first
to thank all the organizers
for arranging this like wonderful conference for us and a chance to meet and share the ideas. This is my first
first.
time in Germany, and I would like to come back again and visit. So today I'm going to talk mostly about the optimizations and the work we're doing inside like Oracle and University of Belgrade, like in researching and compiler side. So we just go around like some background of what we are doing on and what the code layout actually matters, like why it matters, how we arrange code in our programs, and see like how it can impact like our everyday applications that we use. So what does this title even mean? So basically, it's kind of a bombastic title. Like it has a lot of words like code layout optimization guided by profiling. But essentially, what it means is, and the main idea I want to get out of this talk and of this is just arrange the data in order in which the CPU processes it. And just keep this idea in mind while we go through the talk because it's actually a pretty simple idea that can lead real world results. Now, some background. So usually our Java applications like execute in the JVM. So we have our app that's written in the Java files. We compile that app into class files, and then those files get
Loaded by the JVM, and the JVM actually executes our program.
so we have another program that's executing
Our
application, and within the JVM we have all the subsystems
that are required for our application to work, like garbage collection, just-in-time compile.
etc. But there's like another model
To
that we
this,
have within
the
the project, which actually enables us to compile our Java applications ahead of time. So instead of like having our app work on a JVM, we can take both our app and the parts of the JVM that we need, compile that into a native executable, and ship it as a single file that has both our application and all the virtual machine subsystems that our app needs to run. So the Graph VM ecosystem, what is it? It's actually just a JDK. It's another implementation of Java. And within it, there is this component of native image that enables us to compile Java applications into standalone applications ahead of time. So we don't have a JVM at runtime, we have a small VM embedded within our application. And that actually improves and yields us like lower startup time and residence set size or lower memory footprint, which is actually ideal for microservices and serverless environment where we want to start fast, use as little memory and compute time as we can, and then shut down fast. But this kind of has a gap between like JIT and ahead of time. So when we have a JIT and the JVM, while the JVM is running our app, it's actually profiling it and recording which parts get executed the most. And then it can optimize our code based on the runtime information it collects like over time. But we don't have this when we compile into a static executable. So we just have like our static analysis, analyze the program, and from that analysis, we can produce an executable. But we can bridge this gap if we give our compiler profiles. So if we kind of have runtime profiles from the app that we are going to compile, we can combine this information with the static analysis and produce a more optimized build. And why does this matter? This actually bridges static AOT with JIT dynamics. So we can have ahead of time compiled app that's a single like executable, but at the same time have some runtime information about the application and about how it runs and behaves during runtime, and enable the compiler to do more advanced optimizations. So how do we do this? Well, first we instrument our binary, and then we just run it on a standard workload or the expected workload. This run will generate some profiles about the program, and then we can build the optimized binary using this information. And this can inform a lot of optimizations like invoicing, branch prediction, and among the others, code layouts. Or more specifically, how our code is physically arranged within the binary. But why does this even matter? So let's take a simple example of an if-else branch and how this code may look like in memory. So every executable has a text section, and that text section is split into OS pages. So whenever an operating system accesses a page, accesses bytes in memory, it doesn't just fetch that single byte from the disk, it actually fetches the whole page that byte belongs to. So our whole text section is split into pages. And those pages contain the physical or the assembly or concrete binary for our functions or methods. Well, what happens when we access a certain method or when the program execution reaches function A? Well, we have to execute that part of the code. So if that page is not in physical RAM, that will cause a page fault. And the OS has to fetch that page from this. Once the page is fetched and loaded into memory, we can execute the code that's on it. So when we call another method, also if that page isn't in memory as well, well, that triggers another page fault, and we have to load that as well. And the implication here is, well, if our methods are scattered throughout the memory, they're causing all of these pages or more generally that is scattered throughout the memory. Every time we access a certain part of memory that's within physical RAM, we're causing the operating system to do all of this work, and we're having
Is scattered throughout the memory in the physical RAM, we're causing the operating before we can proceed with the organization.
Actually,
another interesting thing that actually happens with the OS.
Linux or most modern operating systems don't just fetch a single page when a page fault happens. They usually fetch multiple pages because it has something like a look-ahead mechanism. Because the OS expects, okay, if I'm accessing the page one, well, most likely I'll need subsequent pages as well, so fetch that as well. So what would usually happen if we kind of page on page one, it will pre-fetch pages upfront, depending on how fast the disk is and how the operating system applies the certain prefetch strategy. Now, this may seem good at the first, but what if this else branch never executes? So if this else branch never executes, we just made the OS fetch something that's not needed. And also, if our code is scattered throughout the memory, without any regard to how it's used and how it's executed, we have this waste of space.
So basically, if we don't pay attention to how our code is laid out, we may have a poor page utilization, or again, more generally, if we don't group data or arrange the data in the order in which it's processed, we can have poor page utilization, and which can lead to page faults, and in critical systems or cloud internet, it can lead to added latency. And the effects amplify if our memory budget is tight. So, for example, in cloud, if you are a cloud provider, you want to fit as much functions or applications as you can in a single machine. The less memory those machines use or those programs use, the more programs you can fit on a single machine. So how can we improve this? What can we do if our code is scattered throughout the memory and we just saw, okay, that's not a really good idea? What can we do? Well, we can rely on some information from static analysis. So, for example, if we know full method names,
if we know full meta names, we can kind of group.
No, the volume. I think we hear an echo on you.
Oh, okay. So if we have full method names, we can kind of group code depending on name, and it's actually a pretty good strategy.
You can actually get a pretty good layout. Some more advanced techniques exist, but the static analysis does not generalize well across workloads. So as we saw in the previous example, the static analysis cannot know which paths we've taken on our standard or expected workload for our application. Now there are some PGO profile guided optimization like layouts that group auth methods based on the call graph, and they yield much better results and have much better results in practice. But again, they ignore temporal order. So something may be hot and something may call each other like often, but that doesn't mean that that's the order in which it was executed. So let's take a look at another example. Imagine this to be a call graph of our application. So we have the root method A that calls B, F, and D. B calls C, and then both F and D call method E. So from this, we can infer like how a program executes, but without like profiles, we cannot know which paths are most often taken. So if we add profiling information to this, with call count and timestamps when this particular method was executed in order, we can kind of gain more insight into how our program behaves and optimize the specific code layout for this workload. So let's take, for example, that root method A doesn't even call this part of the branch, so B and C are never called. And when it actually executes, it calls F, it gets timestamp 2, then it calls E, it gets timestamp 3, then afterwards D is called, which calls E again. So from all this, we can see that profiling information can give us some insight into how our code executes, and then we can use that to leverage a better code layout. So for example, let's say that we use a method name to lay out this methods within a program. So with method name, we will get a layout like this, like A, B, C, D, E, F, but we can already see that that's not the order in which they execute. And for example, we have B and C next to A, but they were never called. And if they end up on the same page, we'll just waste that memory. Or even if they end up in subsequent pages, we'll make the OS fetch something for us that's never executed. But let's try another approach. So PGO based on a call graph, it will do a grouping like this. So it will group the most frequently called methods together and then chunk them based on the frequency in which they call each other. So because A calls D like 200 times, it will put those two methods together. And because D calls E like 99 times, it will put D and E together. And this is much better than a method name because we can see here A, D, and E and F are grouped together because they're executed most often. But again, that doesn't reflect the order in which they were executed. So for example, A may call F and then E, and E may call whatever it wants. And D may execute much later during the program execution, but we see that D was put here. So for example, A and D may end up on the same page, but what we actually want is to F to be here because A was called, then F was called. And with this, if we use the same profiling information, but use the timestamp of when the method was called for the first time, we can actually get a similar layout where all the hot methods are grouped together. Same with the previous PGO-based layout, but the better thing is they're ordered in the exact way in which they were called on a given workload. So how does temporal code layout works? What we do is arrange the methods within the binary in the exact chronological order in which they were first called. And the better workload and the better profile information that we have, the better the layout will be. So how we do this? So let's say we have a procedure like A. What we do from our compiler side is we just insert a little snippet that will record the timestamp for this method. And this timestamp is just basically some global counter that gets incremented and written into a slot for A. And then there is the rest of the methods A implementation. So basically from our compiler side, we just insert a small snippet that will record when the method was executed for the first time. And how this record timestamp works is because multiple threads can execute the same program, we just do compare and swap on this timestamp slot and reserve it with -1. We atomically increment a global counter, and then we write it into this timestamp. And for every method that was executed during the profiling run, it will get a unique timestamp of the first time it was called. Now, for this timestamp, we only record it for the first time because that's the time when it was called the earliest. Because what we're going to do is arrange them in the order in which the CPU will process them. And once we have this information, the layout is pretty simple. Take all the methods that have a timestamp that were called during profiling, sort them in the ascending order using timestamp as a key, and then append all of the rest of the methods that were never called during the profiling run at the end. So here's how this may look like. For our example, let's say that in some execution path, A and C were called, and this else branch never executed. What temporal code ordering will do is it will put A and C on the same page, and because B and D was never executed, it will put them towards the end. So when we execute A during our optimized run, because C is on the same page, the OS will fetch that code as well, and we won't because C. And for the else branch, let's say the A was called, but it said, okay, false, and else branch executes during profiling run. Well, what would temporal code order do then? Well, we put A, B, and D close together, and it will put C towards the end. So basically, what we do, we record the timestamp and order the methods in that way, such they are grouped and arranged in the order in which they are executed. Now, to measure all this, we use GraalVM and OpenJDK25, and all the results showed here are compared to a random ordering. So we produce a random ordering, and we compare and normalize everything to that. Now, in the paper, there was an excellent comment about how do you know that this isn't just a artifact of random ordering, and I think I know. There wasn't enough space in the paper to explain it, but what we do is we have a bunch of seeds, random seeds that we and then we measure the variance of all the different seeds. And the variance between them was around 3%. And so we take what's filed that comes within this variance. But to have a stable results and something we can experiment with, we kind of fix the seed to 42. And we use kind of benchmarks. These are benchmarks that are used in GraalVM compiler on every optimization we implement. So whichever optimization gets implemented in GraalVM, it goes through this pipeline where we kind of measure the performance on different workloads and different applications. And we compare 4 different algorithms random, method name, call graph, and first call. So here's how the experimental setup looks like build and run instrumental executable on a standard workload for these applications. We collect profiles, and then we build an optimized executable using that profile. Then we run this optimized executable 10 times. You can repeat this experiment as much as you want, like 20, 30, 40, but after a while you get the diminishing returns like on stability. So 10 to 12, 10 to 20 will do just fine. And aggregate and normalize results relative to random ordering. So why we do it compared to random ordering? Because we want to show that this actually has impact and the order matters. So on different benchmarks and metrics, RSS or the resident set size or how much physically our program takes the memory in RAM. If we just sort the method names, if you just sort the methods by their name, it's actually like 25% faster compared to random. RSD is standard deviation. Best percentage is what is the best case that this ordering achieved, like what is the best overall gain that we had, and what is the worst is like in the worst case how it performed. Call graph, it's much better, it's 43.7% better. And first call is pretty much the same. Now, this doesn't mean that it's better because both results fall within the variance of each other. But we can see that in the best case they perform the same, which is logical. Because if we have hot methods, like what was called most often, and we have timestamps, once all the hot methods execute, they will be in the same, they will be in the working set, they will just be in different order. So this first call won't fetch anything that was unnecessary. And that's why the best percentage is the same as expected. And these numbers, they just fall within the variance of measuring instability. Now for latency, pretty much the same. Latency doesn't change also within the variance. And why? Well, most of these applications actually measure latency and throughput once they warm up. So once all the pages are already in memory, there is no change here. And throughput is actually the same because throughput is also measured when the benchmark warm up. So all the results here fall within the same range. But there is another interesting measure that we use. It's time to first response. And this time to first response is how long it takes the system until we send a request for it to answer with the first valid response. This is also important like in cloud and serverless where you actually want to start up as fast as you can, give the answer as fast as you can, then just shut out. So method name again, about 14% better, call graph 25% better, but the first call is also better than call graph because the methods are arranged in the order in which they're called. So system has to do less work until it gives the first response, and thus it makes this time to first response short. And in best case overall, first call always consistently gets slightly better results or better results than call graph on the time to first response metric. So code layout will directly impact startup and time to first response. So we want to arrange code in the way in which it's called. And this is actually pretty lightweight. The algorithm is pretty simple. What we actually just need is just timestamp information for every method. And we see that it reduces the time to first response without showing any steady regression in latency or throughput. So there are actually some limitations to this. So if we have profiling gaps, or if our workload during the instrumented run is not representative of what we expect to see in production, then we may have profiling gaps. And if we have profiling gaps, some methods won't get these timestamps, and they'll actually end up in the code section, which will trigger page faults and page loading if we don't have them covered within our profiles. And also inlining instability, because in native image, build is not reproducible because it uses points to analysis. So if you build the same executable twice, you may not get the actually same executable. But this inlining instability between instrumented run and the profiling run also may affect the final decisions into where which method that ends up. And some mitigations for all this is to use the call graph overlay. So once we have timestamps, we can overlay a call graph upon it and then propagate these timestamps to callers and use that as well with the timestamps to make a better informed decision about layout. And there's some experimentation with sharing inlining information between two builds to further mitigate against inlining instability. And for the end, like the main idea of all this that can generalize to not just code layout. I mean, this is applied to code layout, but as we said in the beginning of the presentation, the simplest idea from this talk is just arrange the data in the order in which the CPU processes it. And code is also data that needs to be loaded from memory into the CPU for the CPU to execute it. So if you have it in the rough order in which the CPU will actually need it, that can help both the operating system to fetch the correct pages and the bad prediction. And this also applies not only to code, but also to data that we process. Also, if we lay out the data in the order in which the CPU needs it, we can help both the CPU and the operating system. And again, thank you for the time, and thank you for this lovely opportunity to speak here. And
thank you for the talk.
Yeah, thank you.
There's a question for Marko.
Okay, I have a question. Actually, I have two questions. But the first one is, it seems that the timing is not stable in the implementation with respect to threads. So if you have a multi-threaded application, how are you going to distinguish between similar timestamps? Did you observe some kind of temporal misoverlays because of threading issues?
Yes. So the temporal overlays may happen because multiple threads may try to write the counter to it. So I just find it. Like it is. So depending on which thread like gets to the method first, it will get this counter. But as long as the counter variance is within the page size or within the few pages. So if we have like, let's say we have two methods like A and B, and depending on which order they were called, B may come first or A may come first. We didn't observe that much variance within the performance as long as that temporal difference is small enough that the layouting algorithm places them on the same page or next page or next subsequent pages, because the OS will based on
no, I wasn't referring to this specific part, but essentially if you have two threads that have a different set of methods, a purely temporal recording may lead to an interleaving in code layout that is not wanted because the two threads could have different code layouts.
Okay, yeah. We didn't observe that much. I think it comes from actually the physical like, size of the pages and how the OS lays them out and fetches them. It may happen. We didn't observe the standard like a benchmarking suite that we use has some workloads, but they're usually just not task parallelized but data parallelized. So within our benchmarks, we don't have that many benchmarks that are like task parallelized, but data parallelized, and within that, we didn't observe that much variance. It's like two threads that execute. But the mitigation is as long as this time step like temporal difference between them is not too large, they'll end up at the beginning in a rough relative order. Because as long as they end up on the same page or within like few subsequent pages because the OS will nonetheless like fetch like multiple pages from the disk, it's fine. There is no impact on performance.
Okay, thanks.